Everything inside a black hole can be written on its surface. That strange fact is the seed of the holographic principle. In plain terms, a region's physics equals information on its boundary. Not a camera trick, but a deep rule of nature. It hints that space might be an emergent picture, not stuff. Bits live on edges while we feel a fleshy interior. Black holes set the scale because their entropy grows with area. So a two-dimensional skin can count three-dimensional possibilities inside. Stay with me, because one number will make this click. Chalk dust hung as physicists argued about impossible black hole behavior. Jacob Bekenstein asked a blunt question that cut through the fog. If nothing escapes, where does information about fallen matter go? He guessed black holes carry entropy, just like everyday hot objects. But his twist was savage because he tied it to area. Double the radius, quadruple the surface, and entropy should jump. Volume should not matter here, which felt completely upside down. Stephen Hawking then did something wild. He gave black holes temperature. Quantum effects made them glow faintly, as if they radiated heat. If they have temperature, they must have entropy and microstates. Hawking's math shouted a rule: entropy equals area divided by 4. Units are natural here, but the direction is crystal clear. Add matter, the surface grows, and the entropy never decreases. This mirrored the second law, where disorder loves to increase. Only now, the counting lived on the horizon, not inside. That is the punchline. Area counts the hidden interior possibilities. Why should you care about a pedantic entropy rule from gravity? Because it hints that space hoards information on thin boundaries. Your coffee cools by volume, but black holes count by area. That mismatch lights the path to the holographic principle. It suggests our universe might be describable by fewer dimensions. Not less reality, but a more compact way to store it. Like a movie encoded on film, played as living depth. Black holes were the clue, not the whole story yet, but that clue was loud enough to change the field. It forced a truce between gravity, thermodynamics, and quantum mechanics. Area became the scoreboard for information, not mysterious volume. That scoreboard is the heart of the two-dimensional illusion. And it still shocks people, decades after the first hint. It turned a paradox into a measuring stick for reality. Forget mirrors for a second, picture a hollow sphere with skin. The holographic principle says the physics inside equals data on that skin. It is a dual description, not a cheap special effect. Same events, two languages, interior gravity and boundary quantum fields. Why care? Because that swap can make impossible calculations suddenly doable. Gravity in the volume is messy, while boundary theory can be cleaner. You trade curved space for a flat canvas with many particles. The number of bits scales with area, which sets the rules. So there is a finite budget, not infinite hidden storage. That budget keeps gravity from stuffing endless information into small regions. Physicists call this dual view a correspondence between two theories. Each side answers questions the other side finds brutal. Singularities soften, infinities cancel, and quantum puzzles get reframed. A simple picture helps. Imagine a closed room with a wall. Everything happening in the air can be rephrased on that wall. The wall stores just enough bits to replay the entire show. That sounds like compression, but nothing is lost in translation. Two faithful stories exist, interior story and boundary story. Pick the one that makes the math kinder for your question. Black holes force the principle, but it extends far beyond them. It might underwrite why space feels smooth, despite quantum jitters. Because entanglement between bits on the boundary can weave interior geometry. That is the radical payoff. Space could be bookkeeping for relationships. We will make that vision crisp, using one concrete number soon. And that number lives on a surface, not in the middle. Once you see it, the picture refuses to leave. Time for the number that grounds this wild-sounding idea. Physics gives a smallest area scale, called the Planck area. It is tiny, about 2.6 times 10 to the minus 70. Square meters are huge compared to that, unimaginably huge. Now the holographic rule says, roughly 1 bit per Planck area, so a square meter can store about 10 to the 69 bits. That is a mind-bending density, like a cosmic solid-state drive. Swap square meter for horizon area and you get black hole entropy. Take a black hole with the sun's mass, radius about 3 kilometers. The area is around 110 square kilometers, give or take. Divide by the Planck area and you get about 10 to the 77. That many microstates can hide behind that smooth, dark surface. No more, because the surface sets a hard storage budget. Notice the pattern: doubling radius quadruples bits, not eightfold. area rules the count while volume stays a spectator. This is the immediate operational meaning of the holographic idea. You can estimate information limits using surfaces, not interiors. That guides how extreme matter or quantum fields can behave. It even constrains the ultimate resolution any physical device can reach. Try to stuff more bits inside, the horizon must grow accordingly. Nature enforces the budget by enlarging the surface, not packing harder. That is the number-driven click, and it changes your intuition. Engineers love hard limits because limits tell you what matters. Here, the surface is the thing that carries the price, and the price tag's read in bits, not in meters. Silence holds the debris, while faint shards drift like slow snow around the wreck. The surface is calm, but it remembers everything that fell into the dark inside. Then came a breakthrough that gave holography real mathematical teeth. Juan Maldacena proposed a bold equivalence between two different worlds. Gravity lives in a curved volume, shaped like a cosmic bowl. A quantum field theory lives on the bowl's outer rim. Every event inside maps to something happening on the boundary. Every boundary fluctuation maps back to motion in the interior. No gravity on the rim, full gravity deep in the bowl. Two languages, one story, checked by thousands of non-trivial tests now. This example uses negative curvature, called anti-de Sitter space. Our universe is not that, yet the duality is invaluable. Hard gravity problems become manageable quantum problems on the edge. Black hole interiors match up with hot fluids on the boundary. That gave new insight into quark soup created in heavy ion collisions. Physicists measured a viscosity to entropy ratio near 1/4 pi. Holography predicted that scale, not as a law, but a guide. Here is the trick that matters for understanding the illusion. Entanglement on the rim dictates smooth space in the interior. Cut entanglement links and bulk distances start to blow up. Add links and regions glue together into a navigable geometry. Ryu and Takuyanagi turned that idea into a precise recipe. You draw a minimal surface in the bulk to read entanglement. Area of that surface equals boundary entanglement in those duality examples. So the same area obsession returns, now as geometry from information. Close your eyes and imagine space as relationships, not coordinates. Those relationships live on a boundary, yet conjure a deep inside. That is the holographic principle working, with math guarding every step. Researchers cross-check with numerics and the maps keep lining up. The bowl picture is a tool, not a literal universe. But it shows the illusion can compute real, measurable properties. And that earns the idea a seat at the table. Here is the part that feels like science fiction, yet real. Space may emerge from patterns of quantum entanglement between boundary bits. Entanglement means two systems share correlations stronger than classical limits allow. Those links act like scaffolding, telling geometry how to connect. Rip enough links and regions drift apart into distant places. Add links and tunnels appear between areas that seemed separated. Mathematicians capture this with networks that look like branching webs. Flow along the web and you recover distances and curvature. There's another twist: error correction seems built into holography. Lose a few boundary bits and the interior still reconstructs. That robustness explains why black hole information is not easily scrambled. It hides, but it is not gone, just redundantly stored. Experiments hint at this architecture in small, controlled quantum systems. Researchers teleported quantum states through circuits that behave like tiny wormholes. It was an analog, not a literal spacetime tunnel, but suggestive. The math that encoded the teleportation matched holographic error correction patterns. Small chips do not build universes, yet they test building rules. They show how relationships can store places and protect information. That picture resolves a fear that holography is merely philosophy. It is a working engineering model for how space keeps its books, and the recurring actor is entanglement, not pixels in a grid. Pixels mislead you here. Relationships are the actual storage units. That is why the two-dimensional illusion can still feel thick. Depth is how those relationships organize, not independent, floating stuff. Geometry becomes a ledger, updated by who is entangled with whom. Strange, yes, but it keeps making correct, testable predictions elsewhere. A spinning disk hums softly, storing memories as microscopic alignments on a cold surface. Horizons do something similar, except the bits are cosmic and the surface sets limits. Let me clear two popular traps before we end. This is not proof that reality is a computer simulation. Holography is a duality between physical theories, not a server room. And it does not say our world is literally two-dimensional. We live in 3 dimensions, but a boundary can suffice mathematically. Think 2 faithful novels, written in different languages, telling one plot. Now, what about evidence outside black holes and duality labs? Some clues come from extreme astrophysics, where horizons rule behavior. The Event Horizon Telescope imaged a bright ring around Mate 7's monster. That ring size tracks the surface area, which encodes information capacity. Gravitational wave ringtones also carry the same area-based bookkeeping. When 2 holes merge, the final area exceeds the sum. That respects the entropy rule baked into holography every time. Meanwhile, tabletop analogs mimic horizons with sound, light, or fluids. They radiate Hawking-like quanta, supporting the thermal story. Are we done? Not even close, because our cosmos accelerates outward. It looks like de Sitter space, not the bowl used above. A full holographic map for that case is still unfinished. Yet hints appear, like entropy bounds for cosmic horizons in expansion. Whatever the final form, one practical rule keeps paying rent. Count bits with areas, not volumes, when gravity and quantum meet. It says a square meter tops out near 10 to the 69 bits. That bound flows into black hole thermodynamics and cosmic bookkeeping. It steers designs for quantum sensors and thought experiments about spacetime. It even limits how fine reality can be probed in principle. So the illusion is not fluff, it is a working constraint. And constraints are where real science turns sparks into engines. That is why physicists keep pushing this, through controversy and confusion. The math is hard, but the message is crisp. Surfaces set limits, and limits steer theories toward the truth. That North Star keeps explorers from getting lost in beautiful abstractions. Evidence piles slowly, but the direction keeps pointing there. Bottom line, a surface can hold the story of a space. Black holes taught us that, and the idea kept growing. Holography is not decoration, it is a tool that computes. Entanglement supplies the threads, weaving distance from pure relationships. The picture is strange, but it keeps matching real numbers. If that clicked, you just felt space flicker into something deeper. Want more mind benders like this? Subscribe and stay curious with me.